I'm very happy to be here and welcome to everybody who's online. So, so today I wanted to tell you about density matrix embedding theory, which has been proposed 10 years ago by Garnichan and Gerald Knizia. And for me, it was clear from the beginning that there was something interesting to look at from the point of view of one RDMFT. And I'm not an expert at all in one RDMFT, but that was my motivation. And I'd like to share with you some thoughts and some ideas. So the second part of the talk will be a bit experimental. So I got help from Sadia Luz, who's postdoc in our lab, and he has some background in physics of open quantum systems. And you will understand later on why this turns out to be quite interesting and useful. Okay, so some basics about the density matrix embedding theory. So the whole idea is like you have a system. So it started with the Hubbard model because that comes back from condensed matter physics and the dynamical mean field theory. But actually you could do that also for a molecular system where you have some orbital bases, localized orbital bases or sites, okay, for a lattice. And so that's what these dots are, representing basically, excuse me, yeah. So that's what these dots are. And I pick up a fragment. So here I have four spin orbitals. And so obviously, when I want to compute the total energy, I need to evaluate the 1 and 2 RDMs, expectation values. And it's obviously out of question of solving a Schrödinger equation just for the fragment, you know. This is not possible because that is actually an open quantum system. And of course, it's entangled with the environment, okay? So that fragment has an environment. Otherwise, it would be too simple. So the suggestion that is made in DMET is to perform a unitary transformation in the one electron space, in the spin orbital space. And that's what I represent this on this drawing. So this unitary transformation has to leave the fragment unchanged, okay? But many things happened around. So you see it, so now it looks like a little bit a mess because the representation has changed. And there are some spin orbitals that are represented close to the fragment that is called the quantum bath. So it's a selection of spin orbitals. I will come back to that. And then there are other spin orbitals in blue that corresponds to what I will call later on the cluster's environment. So there is the environment of the fragment that was in black, and then there is the environment of the cluster that is in blue, which is not the same thing because they are not defined in the same representation. Okay. So the basic idea of DMET is to say that, well, in principle, my fragment is exchanging electrons with all these spin orbitals, but I'm going to reduce the size of the system. I will treat with a pure state, a pure wave function with quantum chemistry methods. So basically that cluster, as we call it here, is made of the fragment that we call then impurities. And these impurities are embedded into this bath, which on my drawing consists of exactly the same number of spin orbitals. So the number of impurities is the number of spin orbitals in the bath for a reason that I will clarify in a minute. Okay. So you actually, in the exact area, that system has no reason to be closed in general. I will come back to that as well. But in DMET, you close it, okay? And you evaluate, so you solve the Schrödinger equation for that small cluster that you can afford. That's the magic of it, that's all the interest. And then, of course, you can, from the density matrices you get from this cluster wave function, correlated one, you can evaluate local density matrices. So you have a local evaluation of the energy, which is supposed to be a relevant choice for strongly correlated systems. Okay, so now some words about this unitary transformation that creates this bath, okay? So recently we tried to design or present a unified like derivation of this, because you can approach the problem from very different perspectives. So if I write down the unitary transformation matrix in the spin orbital basis that achieves this separation into a cluster and its environment, this is how it would look like. So you, of course, as I said, you don't change anything in the fragment, but you perform a unitary transformation in the environment of that fragment. Okay. And what we found out recently is actually it's quite simple to define not the bath, but the environment of the embedding cluster. It's actually something much simpler to do. And so the whole idea is like you have the density matrix of the one RDM represented in the localized basis. And the only thing you need to consider is this block here, which is the environment fragment block. Okay, so you have the number of columns is the number of impurities that are inside your fragment. And basically what we call the environment of the embedding cluster is just the set of vectors that are orthogonal to this to all the columns of this environment fragment block. It's as simple as this. So by doing that, you define the environment of the embedding cluster, and implicitly, of course, the remaining part of the space will be what we call the bath. How you proceed, the bath orbitals might be different, but the subspace is exactly the same, and that's the only thing that matters, of course. Okay, so the simplest case you can consider is you embed a single impurity. So then the environment of the embedding cluster is orthogonal to that vector, which means that that vector is actually the bath. Okay, so so in other words, if you want to construct the bath orbital in that case, you just pick up the density, the 1RDM density matrix elements in the localized basis, and this elements are the coefficients that you have to put in front of all the environment orbitals of your fragment. And here is the bath. That's okay, as simple as that. Okay, so of course, if you have more impurities, that subspace will have the dimension of the subspace of the fragment. So that's why there are as many bath orbitals as the number of impurities. And well, you're completely free to decide what basis you use inside that subspace. So in regular DMET calculations, people use a single value decomposition of this matrix block here to generate the basis. We use another one, which is called the block Householder transformation, but all in all, it's the same subspace. So there's no difference, okay? The bath is actually a subspace, a spin orbital subspace. All right, so now the important question is, when is this strategy exact? I mean, the fact that we isolate a cluster from its environment, you know? So it turns out that, so if you're a reference density matrix, and I should insist on that, so that density matrix is the only density matrix, the only quantity that you will evaluate at the scale of the full system, okay? And that's your reference. You're using this to design the embedding, okay? So if that density matrix is idempotent, then the embedding procedure is exact. So you can show that basically you can identify a block in the density matrix whose size is twice the size of the fragment because it contains impurities and bath. So that block is completely decoupled from the rest of the system. And you can also show that it contains exactly an integer number of electrons, which corresponds to the number of fragments or of impurities. Okay, the dimension of the fragment space. Okay, so it's super nice because there is a simplification here at this level. And that's nice, and that is used as a basis to start the correlated treatment. That's that's basically the whole idea. Okay, so that's exact. Basically, if you describe a non-interacting system or if you perform a mean field calculation. Okay, that's what is done in practical DMET calculations. Okay, so, but now, of course, you want to correlate. So once you've been through this step that you rely on a kind of mean field or non-interacting full size calculation, which is usually called the low-level calculation. On that basis, so you have defined your embedding cluster. And now you can say, I will restore interactions inside that cluster. And this is how I will be able to correlate, okay? So in the single impurity case, you would simply, turn on the interaction on that impurity. So this would essentially be the U of the Hubbard model if you are on the lattice, okay? And when you do this, of course, now you are entering the world of approximations because the whole procedure was exact for a non-interacting case of mean field, and now it's not because the interaction has been introduced. So, for example, what you can immediately look at is the occupation of your impurity when you turn on interactions, okay? As you would expect. So that's for a Hubbard ring. So when U is 0 in non-interacting case, basically you get what you would expect, the exact result, the occupation is exact, okay? But as soon as you turn on interactions, you see you have a deviation from the exact result, which is not a big surprise because now this site is interacting and it was not in the design of the embedding, okay? So that's common in most embedding approaches. So how do you cure that? Well, people introduce a chemical potential on that impurity to balance the effect of the interaction. So of course, what I should say at this point, the motivation of this presentation is to answer, try to answer a question like, can we make this procedure exact for interacting electrons? Okay, that's the question I'd like to ask. And I'm not going to bring a definitive answer to that, but yeah, let's try to see where we go. So as a kind of first answer to that, so recently we found out that it is possible, we made the derivation for a Hubbard lattice to connect actually this chemical potential, which is a bit introduced a priori, it's an ad hoc thing that you realize you have to do. Actually, we found out that you can find an exact relation with the Hartree exchange correlation potential that would exist in the full size non-interacting system that created the embedding cluster, which means that if you adopt this point of view, the low-level calculation, as it is called in DMET, is becoming actually a Kohn-Sham calculation. So that's a way to exactify the approach from the point of view of density functional theory. So you rely on a full-size Kohn-Sham system, and that system will create the embedding, okay? So I'm not showing the contributions that are added, but you can really identify terms, functional derivatives of the density, and you can explain what they are physically and so on. Okay, so that's what we actually did in this paper here. Okay, so from the point of view of density functional theory, there's therefore a possibility to really exactify that approach, which is kind of nice. Okay, but yeah, and one thing I should say, because Hardy in his talk on Monday was wondering, is it a curse or a blessing to have a universal density functional? If we adopt this strategy now, it's really different because there are actually no functionals. And the hope is that this will give more no explicit function of the density. So the hope is that we can actually improve a kind of implicit function of the density for a specific system. So at first sight, it's like there's more flexibility in the improvement of approximations, which is kind of interesting, I think. Okay, but nevertheless, in practice, the MET practitioners are not only interested in the density and the occupation of the impurities, they want more, and because there's more information to use. So when they correlate inside this embedding cluster, now they get a correlated fragment block of the density matrix. And what they usually do, they try to map that one onto the density matrix that you get at the mean field or non-interacting level of calculation on the full lattice. And there, of course, if you do this, then comes the important question, like, well, you're trying to represent the correlated density matrix with an uncorrelated one. And as Hardy mentioned on Monday, you know that this object is idempotent, okay, while the other is not. So it's not going to work, okay? So it's always done by minimization of a cost function, but then the answer remains, like, can we map in one way or another the correlated density matrix onto this full-size system? Can it remain non-interacting? Obviously not, or we have to do something, okay? So this is a kind of question that is important because you clearly benefit from the fact that you are also taking into account the off-diagonal element of your correlated density matrix. So how to make this kind of consistent, you know? That's the question I'm asking. Okay, so what we've been trying to do recently, I was like, the embedding is very nice formally when it relies on the idempotency of the density matrix. And I think this is important because, so I was simply wondering, could we preserve that property, you know, but still find a way, so an indirect way to introduce correlation in this picture beyond what we do in DFT, you know? That sounds like a stupid question, but we'll see. So very briefly, this idempotency thing, of course, usually people work with the Hermitian one electron Hamiltonian, obviously. And when you diagonalize it, you get this clearly idempotent representation of the density matrix. And this is why now if you go back to the localized orbital basis or lattice representation, you get this full density matrix that you can exploit for designing the embedding cluster. Okay, that's the whole idea. But still, that matrix is idempotent. Yeah, so that's the key ingredient in the embedding. Okay, and then came this idea to say, how could I possibly preserve idempotency, but still try to get more information packed into actually the one idea. So I don't know, I will not tell you the full story, we can discuss, but then I came to this idea because I was thinking about the current, and then at the end I realized, okay, what happens if we introduce an anti-emission correction to the Hamiltonian? So this is a very dangerous territory, but okay, let's try to see. So if you do this, of course, now you have to be very careful because you can diagonalize your one electron Hamiltonian. But well, the first thing to do is you have to be sure, it would be nice that you keep real energies, of course. That would be nice, like in PT symmetric Hamiltonians. And then you also have to be careful that actually your creation operators in this representation are not the adjoint of the annihilation ones, because unfortunately you have left and right solutions because the Hamiltonian is not Hermitian anymore. So you have to deal with that, okay? But well, still at the end, I would say like in coupled cluster theory also, you have a non-Hermitian Hamiltonian. But at the end, it's still nice that in this new representation, you still keep this structure, okay? So you still have an idempotent density matrix, but you have to be clear that it is idempotent in the bi-orthonormal way, okay? Because you have left and right solutions. All right, so basically now if I rewrite the full one RDM into this localized basis, if I come back to the original basis, of course, the density matrix will not be symmetric anymore. And we could see that as a problem because it's not physical. Now the question is, can we actually benefit from this? Can we store more information about the correlated one RDM into that density matrix? So it's a question that I'm just asking. So let's do it step by step. If I start from this density matrix, which is not symmetric, of course, I can proceed with a symmetrization to start with. And then I would get, I guess maybe I can ask about representability and so on, but I have a density matrix, okay, that is at least symmetric. And what's interesting is that that density matrix is clearly the true one if you're treating, let's say, a non-interacting problem or a mean field problem. So what I mean by this is if you just think about Kohn-Sham DFT, for example, we always write, of course, the variational principle and we minimize. But if you now think in terms more about a stationarity condition, if you search for left and right eigenvectors, automatically you will get them equal and they will correspond to the Kohn-Sham determinant, okay? Because none of these terms here will introduce a deviation from hermiticity. Okay, so, but then it means that, of course, I don't have any density matrix functional description of electron correlation. It goes through the density, all right? So the deal is like, okay, but imagine that I can actually introduce deviation from hermiticity. Then I was thinking like, if we use that, thinking of it as a Kohn-Sham density matrix, and we want to go beyond that to create a density matrix that is not idempotent, for example. Well, I could actually benefit from the non-hermiticity of my non-interacting, non-Hermitian 1RDM. So what I'm wondering is, can we actually exploit the difference that would appear between these two upper and blocks of the density matrix to encode more information and introduce that way, so create that way, a kind of density matrix. Is it physical in terms of representability? I don't know, but at least it would be more physical. It's symmetric and it would contain in one way or another some correlation, okay? So this raises two questions. The first one is, can I make that exact? Can I map really the full density matrix? If I can do that, am I able to construct a variational principle? So if I want to do this, it means that I have, so just to be clear, what I call delta gamma bar is the difference, it's the difference between these two blocks. Okay, that's the deviation from hermeticity. So if I manage to introduce somehow a functional that depends on this deviation, then I will get an equation where I will introduce basically deviation from hermeticity. But I have no idea what this functional is. I suspect that there's a connection with the phi xc that Hardy talked about in green function, and then the derivative would be a kind of self-energy. That's probably a connection if this works. Yeah, almost down. And but that's a completely a question. And the other question, of course, is can you really map the density, a correlated density matrix onto this system? So just to answer that, so Sadyalus used this program quant and body that can actually tackle non-Hermitian Hamiltonians, and we just made, as it's done in the MET, a minimization of a cost function for some simple Hilbert orderings, just to see if actually we can get something out of it. So it's quite experimental, but I was just wondering. So if you look at the symmetric Hilbert dimer, you can do this by hand. There is no problem. You can map exactly in this indirect way the density matrix for any correlation regime. So you see, well, that first of all, the energy always remains real. There's no imaginary part, so it's safe. You get an exact mapping, but that you can show also analytically. And for example, if you show the correlated kinetic energy, you get it perfectly right. So the encoding is exact that way. You can make it exact. If you deviate from the symmetric case, you get exactly the same features, so it's fine. So if now you take a larger system, like 4 sites here in this case, then you don't get exact mapping anymore. But nevertheless, the energy remains real, no problem. You get a decent mapping, and if you compare, you see this is the non-interacting kinetic energy. This is what you would get with this non-Hermitian, non-interacting system. So you clearly catch kinetic correlation energy that way, which means that the idea is not completely stupid. Okay. And you get the same feature more or less if you asymmetrize the system. Okay. So, so the natural question now for the discussion is like, are we going somewhere with that? Is there something I missed? I was thinking about the hyper complex Concham DFT we heard briefly about in the previous talk, because there might be a connection there. I don't know. So yeah. Anyway, thank you for your time.